So on Monday we started talking about sets. Okay, talked about the fact that sets are pervasive in mathematics, and as the author puts it, everything in mathematics can be described using sets. Okay, so we started talking about what does it mean to be an element of a set, the notation for sets, so we're going to talk more about sets in chapter 1. We finished section 1.1, but I wanted to do a couple of examples from the book. Let's see. So you have I did assign some homework, and I posted that homework assignment on Blackboard. Let's look at. What's this? I don't know how I can't get the board there. So, you guys see those? Do you guys have your book? Some of you talk about bringing your book with you, or you don't have a copy of it, all of you, right? So you guys have to write this on the board. So I want to do number 19. One second there. Okay, so we talked about one way to write a set is in set builder notation. Okay? So this example, you have a set written, and it's not very precise because you have all these dots, okay? So how would you describe the numbers in the set using words? What would you say if you had to describe these numbers in sets? That's kind of a way to help you rewrite it in set builder notation. If you can describe this in words, then you could probably convert it to set builder notation.
Integers.
They're integers, okay. Multiples of 3. Okay, so these are all the integer multiples of 3. You guys agree? So that would give us a way to write this in set builder notation. Okay. You could say, you could do this a couple of ways. You could say, remember, bold Z is for integers, right? So it's all a set of all integers such that n is a multiple of 3. Right, you could actually write a sentence like that.
So could we say something like 3n?
Sure. So you could say, so every single thing in here looks like 3 times an integer. Okay? So you could say your arbitrary object that's in here looks like 3n, where n is an integer. It's another way of writing it. Okay? But both of them are correct. As long as, what does it mean to be a multiple of 3? It means 3 times another integer. Okay? So we'll talk more about this later. Like, what does it mean for a number to be even? It's a multiple of 2. Okay, well, how do you write it? It's 2 times an integer. Okay, so here's a couple of different ways you could write this set in set builder notation. Okay, any questions with that? All right, let's do. I've written down here. Get some drawbacks to using this webcam. I can't see the video and the book at the same time. Okay, how about this? This is number 26. Dot, 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 127, 19, 1/3, 1, 3, 9, 27. You probably recognize this has something to do with 3 as well, right? Each element of this set. How would you describe it?
3 to the x such that x is an
Okay. So these are all powers of 3, right? Like 3 to the first power, 3 squared, 3 cubed, and then even these fractions, 1/3. Think of that as 3 to the minus 1 power. This is 3 to the minus 2 power. 3 to the minus 3 power. 1 would be 3 to the 0 power. Okay, so think about your exponent rules. So I would, everything in the set looks like 3 to a power. So 3 to the x, sure. And then such that this is ranging over all possible integer exponents. So x is an integer. Okay? Any questions? Okay. How about problem number 44, 1.1. Okay, so the set has elements that look like this, parentheses x comma x squared, such that x is a real number. All right. So, is it obvious what this set is? Oh, okay. The direction is actually, sorry, I need to tell you that, right? This is just a set. Probably looking at it, well, okay, that's great. Okay, so the directions say sketch the following sets of points in the xy plane. Okay, so sketch the points. Okay. So x will range over all possible real numbers. Okay? So think of this as points in the plane. The x-coordinate can be any real number. The y-coordinate, the second coordinate here, is the square of the first coordinate. So maybe we should start with like just a few points. So x can be any real number. So like, what about 1? X could be 1, right? If x was 1, what would x squared be? 1. So the point 1, 1 is actually in this set. What if x was 2? 2 comma 2 squared. So that would be the point 2 comma 4. What about 0, 0? 0, 0 is in this set. 0 squared is 0. About negative 1. Negative 1, 1 would be in the set. The square of negative 1 is 1. What about negative 2? Negative 2 squared is 4. This starting to look familiar? Yeah. This is a parabola. All these points lie on this parabola. It's this kind of the standard parabola. How are you used to describing this graph? Okay. So we have different ways of describing, what we call functions. Fx equals x squared, or simply y equals x squared. Right? You guys have graphed functions before. So this is an example of, maybe you don't think of functions as sets of points. But a lot of times, when I teach functions, that's kind of the way I define a function. A function is, it's a relation. A relation is just a set of points. A function is a special relation where no two x-coordinates have the same y-coordinate. Okay? But any graph that you've drawn in any class, you can think of it as just a set of points. Okay, and so now we have a way of drawing or writing these things as in set builder notation. A set of all points that look like this, where x is any real number. Okay, so you can see the connection between like calculus or pre-calculus and set theory. You can think of graphs as that are just sets of points. Okay. So I wanted to show this example to show you that really mathematics. You might have thought, well, how's calculus all about sets? Well, here's the calculus studies. You study functions in calculus, and here's every function you represent as just a set of points. Okay. All right. Any questions so far? So this is just kind of a little review of what we did in section 1.1. So today, my goal is to cover the next couple of sections of chapter 1. Section 1.2 starts with another type of set called the Cartesian product. That's basically, you think of it as, how would you multiply two sets? This is one way you could define, I guess, like a multiplication of sets. Okay. So this is section 1.2, the Cartesian product. All right. Look at this. Parentheses 2, comma 3, parentheses. So what is that? It's an interval. We talk about intervals as sets, subsets of the real line, right? So it could be an interval. What else could it be? It could be a point in the xy plane, right? What if I did this? 2, negative 3. Could it still be an interval? You say yes, you say no.
Not really written traditionally.
Well, by convention, you write the left endpoint first and the right endpoint second. So, this would not be, if you intend this to be an interval, it would be, incorrect, because if you're trying to say all the numbers that are greater than 2 and less than negative 3, that's the way you'd have to read that, and it's really the empty set. But, so, this, by connotation, you should be able to tell whether we're talking about an interval or a point, or something else. I mean, so this is the Cartesian product of two sets. Sometimes you can get objects that look like this. What we can call this for sure is an ordered pair. So if I saw a 2, negative 3, I would think it's probably not an interval, because you wouldn't have negative 3 at the right interval for an interval. Okay. So what is it? It's an ordered pair. So a pair, because there's 2 numbers, it's ordered because just like in when you're looking at points in the plane, 2, negative 3 is different from negative 3, 2. Right? The order matters. Okay. So an ordered pair is just basically a list of 2 things, separated by a comma and surrounded by parentheses. Okay. So we saw that sets could have anything in them. You could have a set be an element of another set. If you have any object, it could be an element. So you could have for ordered pairs, it just has to be 2 things. The most common ordered pairs we see are points in the plane. Okay. So we have an ordered pair. Let's look at some sets. Okay. A is a set containing the 1, 2, and 3. B is a set containing the letters X and Y. And I'm going to form ordered pairs from the elements of A and B. The way I'm going to do it is I'm going to take the first coordinates from A and the second coordinates from B. What you end up with is what we call the Cartesian product. You talk about like A cross B, or you can say the Cartesian product of A and B. So I'm going to list it out, what this set is. It's going to be a set of ordered pairs. Okay? So every element inside A cross B has a set of parentheses separated by a comma. I'm going to take first coordinates from A, so like 1, and the second coordinate is going to come from B. So 1x is an element of this Cartesian product. The other elements are 1, y, 2, x, 2, y, 3, x, and 3, y. So this is the Cartesian product of sets A and B. It's a set of all ordered pairs where the first element, the first coordinate is an element of A, and the second coordinate is an element of B.
So kind of just distributed.
one of the sets into the other?
Well, yeah, it's something. We did something. It's not. I don't know if you want to use distributive or it's almost like a. I mean, it's almost a type of multiplication, but we're building. Starting out with sets and generating new sets. Okay, so we'll do that a lot today. Talk about subsets and other ways you can combine sets to get new sets. Okay, so A cross B, you take all ordered pairs where the first coordinate is in A, second coordinate is B. Here's the more formal definition. Give an example. Let A and B be sets. The Cartesian product of A and B is the set, right, A cross B. What is in the set? So they're ordered pairs. Okay, so there's the kind of the arbitrary object that's in this set. So everything in the set is an ordered pair, and the first coordinate A has to be an element of set A, and B, the second coordinate, has to be an element of set B. Okay. All right. Any questions about the definition so far? Now let's talk about the size of this set. So if all the first coordinates can be elements of A and all the second coordinates have to be elements of B, let's think about how many of these ordered pairs can you get. On the last example, my set A had 3 elements, set B had 2 elements, and A cross B, the product had how many? 6.
Cardinality of A and B.
Yeah, you can, if you take, if you take one of these elements and one of these elements, make a point, make an ordered pair. So how many can you have? You have 3 times 2, and you can get the order of A times B. Okay. So if there's a fact that the order of the Cartesian product of A and B actually equals the order of A times the order of B, or the size, or cardinality. Okay. You have this many choices for the first coordinate. You have this many choices for the second coordinate. You multiply this number times this number, and they give you all the number of possible ordered pairs that you can make. Okay. Make sense? That's why we had, in the last example, we had 3 elements of A, 2 elements of B. That were 3 times 2, 6 possible ordered pairs we could put in this set. All right. So common Cartesian products. You've probably seen this. Let's see some examples. You've all seen this. I'm 100%. What about the Cartesian product of the real numbers with the real numbers? You've all seen this. In fact, the last example I had on the board, I used this set. So think about it. It's, by definition, it's a set of all ordered pairs, x, y, such that x and y are real numbers. So what's another name for the set of all points where the x and y coordinates are real numbers? The plane, yeah, the xy plane. This is just the xy plane. XY. Or the Cartesian coordinate plane. So you guys know where the name Cartesian comes from.
French guy that invented it.
Yeah, some famous dead French guy. So there's René Descartes, was a French philosopher and mathematician. He came up with this idea of the Cartesian coordinate system. Actually, the story goes, he was laying in his bed and he was watching a fly walk across the ceiling, And he noted if he could tell the distance from two perpendicular walls to that fly, he could tell the exact location and map the movement of a fly. And so he came up with this idea, and it revolutionized mathematics. When you could study geometry using algebra, it revolutionized mathematics. And so this is one of the greatest inventions of history, of mankind, in my opinion. But so the XY plane. It's probably a more common notation. Instead of R cross R, when you use the same set times itself, often we'll just write it as R squared, right? Instead of like X times X, we use X squared. It's kind of common notation. So the most common notation for the XY plane is R squared. So it stands for the Cartesian product of real numbers with itself. Okay.
Is R squared though, if you only have positive values?
No, it's because this is not an exponent in the sense that it's literally a number times itself. Okay, it just means you're taking a new type of multiplication, the Cartesian product, R with itself. Okay, so it's not now. If some people, if you want just the positive real numbers, it's kind of you can do something like this. Some people have done this. I've seen this in class like R with a little greater than 0 sign, but this is more. I used to say it's standard, but we're not really. I don't really want to talk about that. So this doesn't mean all positive real numbers times themselves. It's just a symbolic, because we use exponent 2 for something times itself. Okay, it's a different type of multiplication here. Mm-hmm. Yeah, I mean, mathematicians are notoriously lazy, and we have symbols for everything. And someone the other day, I remember somebody asked me about such that. When we start writing proofs, we use the word such that all the time. Like this colon. Remember, I told you you can read that as such that. It's like the set of all ordered pairs A, B, such that A is an element of A, B is an element of B. Okay, so such that I use S period, T period a lot. So when we get to proofs, if I write that on the board without explaining it, that's what I use a lot for such that, just S period, T period. Okay. Some people will use like a backwards element. You know how we use A as an element of capital A? If you use a backwards epsilon like that, some people use that for such that, but I don't see that as very often. So we come up with notation for everything, just so we don't have to write it. So it's R squared is a little bit easier than writing R cross R. Okay. All right. How about C cross Z? So, what would this set look like if you graph this set? So by definition, it's a set of all points x, y such that both coordinates are integers. Right? A set of all points x, y such that x and y are both integers. So what does this set look like if you were to graph this set? So here's the XY plane. What are the points whose coordinates are all integers, or both integers? What's it going to look like?
Kind of like a scatter plot.
Kind of like scatter plot. Okay, so like a bunch of points. So yeah, let's give some examples. Like 1, 1 would be in this set. It's a grid, or sometimes we call it a lattice in mathematics. Call it a lattice. Call them the lattice points. Have you ever seen like structure of like a salt molecule or something. There's like points and sticks. I mean, so it's basically what it is. You're getting a grid. You know, and it's like 0, 0, 0, 1, 0, 2, 0, and so you get, so you get this lattice covering the whole XY plane. Okay. So I would actually call these lattice points. How about the set R cross N? So the real numbers, the product of the real numbers and natural numbers. Okay, remember the natural numbers are like positive integers, so 1, 2, 3, 4, 5. So what do these points look like? Okay, so they're a set of ordered pairs, x, y, where x is a real number, but the y coordinates are all natural numbers. Okay, so the y coordinates are only allowed to be numbers like 1, 2, 3, 4, 5, and so on. So what would this look like? If the y coordinates can only be 1, 2, 3, 4, 5, and so on.
Bunch of horizontal lines.
Exactly. It's just going to be a bunch of horizontal lines. Because the x coordinate can be any real number. So it's basically like copies of the real line, just a bunch of horizontal lines. So you'll get horizontal line at height 1, horizontal line at height 2, horizontal line at height 3, horizontal line at height 4, and so on.
So if you reverse the order and did natural numbers cross real numbers, it would be vertical lines instead?
Exactly, because since the ordered pairs, the order matters, then the first coordinates would be natural numbers, so they'd be natural numbers to the right of the y-axis. It'd be like a line at 1, line at 2, line at 3, line at 4. Okay. All right, any questions? Any questions? Okay. So I didn't define the Cartesian product of 3 sets, but if you guys take Calc 3, you'll run into this set, R cross R cross R. So this is what we represented by 3-dimensional space. So instead of an ordered pair, you have ordered triples, we call them. So if we set the points x, comma, y, comma, z, usually the common letter we use for the vertical axis. So x, y, z, such that x, y, and z are real numbers. So you can extend this to any number of sets, but again, this is always represented by as r to the 3rd power, r cross r cross r. Okay, so you just think of this as 3-dimensional space. Okay, so if you could have higher dimensions, but you can't really visualize above 3 dimensions. I mean, so my PhD dissertation, I worked in geometry in higher dimensions, in any dimension. You could define angles. It was working on defining angles. How do you define an angle in higher dimensions? Okay, so you can just basically after this point you can just keep adding coordinates. You could have coordinates with points with 4 coordinates or 5 coordinates or whatever, and so you're in higher dimensional space, and you just deal with equations or inequalities instead of pictures. You can't really draw a picture of 10-dimensional space. So, all right. Any questions about Cartesian products? Okay. Then let's look at example before we move on to the next section. These are all pretty much, I think all the examples are infinite. sets. Let's look at a finite Cartesian product. A is a set with 1 and 2 in it. B is a set with 3 and 4. And C is a set with 5 and 6. Okay. So before I write the elements of A cross B, how many elements are there going to be? 4, right? There's 2 elements of A, 2 elements of B, but 2 times 2. Okay, so I'm going to just start kind of systematically. I'm going to use 1, 3, 1, 4, 2, 3, 2, 4. Okay, there's the whole set A cross B. All possible points where the first coordinate is from A, the second coordinate is from B. Okay. All right, how about A cross B cross C? So now, how many elements are there going to be? It's going to be 8. So these are ordered triples. So there's every point has 3 coordinates. The first one comes from A, the second one comes from B, the third one comes from C. There's 2 choices times 2 choices times 2 choices. There's going to be 8 points. So just you got to do it here. So 1, 3, 5. 1, 3, 6. 1, 4, 5. 1, 4, 6. Those are all the points that use 1. Okay? And I'll start with 2. So 2, 3, 5. 2, 3, 6. 2, 4, 5. And 2, 4, 6. Okay. We got 8 points. Must be all of them. Okay. Any questions? Here's a question. Okay. The cross product of a set, of 2 sets, you would make it, the elements of this are going to be ordered pairs. The first coordinate comes from A, the second coordinate comes from B. Okay, so we know what that set looks like. It looks like this. Okay? What if I took this set, A cross B, and took the cross product of this set with the set C? So think of it this way. I need a set of parentheses here to say what define this. So this is, I think of this as one set, the set A cross B. I'm going to take this set and take the Cartesian product with the set C. So we're going to get ordered pairs. Without listing out the whole thing, let's just think about what the ordered pairs would look like. Okay, they're ordered pairs. All the things inside are ordered pairs. The first coordinate comes from A cross B. So it's actually a point, right? It's actually, so for example, 1, 3 could be the first coordinate of this ordered pair. And then the second coordinate just has to be anything from C. So it could be 5, for example. So it's slightly different, right, from the previous problem. How many points are there going to be in this set? 8. Yeah, there were 4 points in A cross B. There's 2 points in C, so 4 times 2 is 8. They're going to look very similar to this right here, right? How will it look different? How does this point look different from this one? Yeah, there's like another set of parentheses inside here. So like I could change this to this set if I added these parentheses like that, right? for each point in that work. So, again, you don't often come in contact with these types of sets, but it's like we saw on Monday. A problem like this would just try to test whether you truly understand the definition of a cross product. Okay, you take order pairs where the first coordinate comes from this set, the second coordinate comes from this set. Doesn't matter what this set looks like or what the things inside the set look like. Just take one of them and put it here. Okay, and then take whatever's in C, whatever those elements look like, take one of them and put it here. Do that over all the possibilities. Okay. All right. So I posted your first homework assignment. So I'm going to decide that all of your homework is going to be due on Mondays. So I'll write it on the board here. But I've also written the homework assignment on Blackboard. So from section 1.2 on page 10, number 2, 10, 12, and 17. Okay, like I said, I have posted this on Blackboard as well. Okay. Let's see here. So we finished 1.2. So my goal is I want to cover 1.3 and 1.4, but I promise you that I try to break up these long classes. I mean, we've only been going for like 40 minutes, but it's a good place to just take a couple minute break. Okay, so let's take a couple minute break. should be back in business here. Okay, so the next section, chapter 1 is 1.3, subsets. A lot of kind of definitions in this class. We're getting the background, the material, the objects that we're going to be proving statements about. I mean, this class, like I told you on Monday, I think the purpose of this class is to learn how to write proofs. And so we need some objects to write proofs about. So we'll write proofs about sets, and so that's why there's still a lot of definitions here. Your exercises you're doing are kind of just trying to test whether you understand the definitions of these objects. Okay, so I realize it might seem like, well, where's the proof? They're coming, but we got to get some objects to prove statements about. All right, so here's two sets. A is set 1, 2, 3. B is set 1, 2, 3, 4, 5. A is a subset of B. Is the word subset? It's kind of used as like an English word. You guys kind of heard that before. I mean, mathematicians. I mean, I use it as a mathematician so much that I think people that aren't mathematicians could probably use the word subset. So what does it mean for that A is a subset of B?
Every element in A is an element in B.
Yeah, exactly. So all these guys are also in this set. So A is a subset of B. That's it. Okay. So A. Let's put it this way. Every element of A is also in B. So A is a subset of B, and here's the notation. It looks like a C with an underline, and I think of it as C for contained. Like A is contained in B. It's kind of the way I think of it. A is a subset of B. Okay. All right. More formally, when you have, so it's going to be, we will have proofs where we have to prove that one set is a subset of another. So I want to be very precise as well in my definition of a subset. Okay, so if every element of set A is also an element of set B, then A is a subset of B, noted A subset B. Okay. All right. So how would a set not be a subset of another?
Like if A was like 1, 2, 3, 6, and B was 1, 2, 3, 4, 5.
Yeah. So let's look at a set. Let's call it C. 1, 2, 3, 6. C is not a subset of B. Here's the notation. You can just do a subset symbol with a slash through it. Okay? So why is C not a subset of B?
Because not every element of C is an element of B.
We can find at least one element, in this case the element 6, that's an element of C but not an element of B. Okay? So that's really the only way a set is not a subset of another is if you can find an element that's in C that's not in B, then it can't be a subset of B. Okay. All right, let's go back here. So if A is not a subset of B, we write slash through the subset symbol. So this, you would read this, A is not a subset of B. So A is not a subset of B means something very specific. It must be true that there's an element of A that's not in B. Okay? So A is not a subset of B means there is at least one element of A that is not in B. It is not an element of B. Okay. Any questions about subsets so far? Here's some examples. Natural numbers are a subset of the integers, right? Every natural number is also an integer. So this is a true statement. A natural number is a subset of the integers. What about the integers? The integers, anyway, it could be a couple sentences here, but how about the integers are a subset of this set. Remember what this is? The rationals, Q for quotient. So the integers every integer is a rational number. So the integers are a subset of the rationals. The rationals are a subset of all real numbers. These are all true statements. How about the rationals are not a subset of the integers. I mean, the integers are important. The rationals, we define them as any number that can be written as a fraction of integers. But not every, like 1/3 is a rational number, but 1/3 is not an integer. So there's an example. I've given at least one element of the rational that's not an integer. How about this? Okay, how about I define a set? Let P be the set of prime numbers. So I'm going to write it like this. How about set of natural numbers such that n is prime. Okay? So P is the set of prime numbers. Alright. Let's write another set. How about this set? A set of natural numbers that are odd. So a set of natural numbers such that n is odd. P is not a subset of the odd natural numbers. Why?
Because 2 is an odd number.
2 is a prime number, and 2 is even. So even though there's infinitely many primes, the one number 2 ruins it. So they're not all odd. Okay, almost every prime number is odd. In fact, an infinite number of prime numbers are odd, all of them except for 2. But that's all we need. We only need one element of this set to not be in this set in order to say that P is not a subset. Okay? Any questions so far? How about this statement? the integers are a subset of the integers. Is that true? Are the integers a subset of the integers? Okay, so take an element here. Take an integer. Is it also an integer? Yeah. So it's actually true that any set is a subset of itself, by definition, right? If every element, think about it, you know, A being a subset of A. So if every element of A is also an element of A, then we would say A is a subset of A. That's a true statement. Okay. How about this? Remember the zero flasher, that's the empty set. The empty set is the set, it's like an empty box. It's a set containing nothing, no elements. The empty set is a subset of the integers. True or false?
True.
So some people say true, some people say false. Let's take a vote. It says true. It says false. It says not sure. Okay, so not everybody voted, I don't think. It's actually true. So, what does it mean? So if you say it's not true, what you would say is that the subset, that the empty set is not a subset of the integers. What does it mean to not be a subset? That means that you have to find at least one element of this set that's not an integer. Can you find an element of the empty set that's not an integer? No, by default, this has to be a subset because there's no elements to mess it up. I mean, there's nothing in here, so you can't find the element in here that's not in here. So it's kind of a, you know, logical argument. You have to think about what does it mean not be a subset of another set. If this was not a subset, then you could find an element of this set that is not in here. But you can't do that, so therefore this has to be a subset of this. Okay? So a couple of things I want to point out with these two examples. Every set is a subset of itself. The empty set is actually a subset of every other set. Okay, so that's a little fact. Maybe I have to write that up. Okay. So every set is a subset of itself. There's the fact. Every set is a subset of itself. Okay, so A is a subset of A. Another fact is that the empty set is a subset of every set. So these are kind of called trivial subsets. Some people will call these trivial subsets. Every set is trivially a subset of itself. The empty set is trivially a subset of every other set. Okay. So any other subset, we call them a proper subset. Okay. So anything other than the set itself or the empty set, we call it a proper subset. Let's do a concrete example here. Let's use a concrete example using abstract symbols. It seems more concrete. Right? If I have a set 1, 2, and 3, let's list the subsets of A. Okay. Well, we start out with the empty set. We know the empty set is the set with no elements, but that's a subset of this. And let's list all the subsets that have only one element. Okay. The set containing just the number 1 would be a subset. The set containing just the number 2 a set containing the number, just number 3. You guys getting better at writing squiggly brackets? The 3s will start looking like squiggly brackets pretty soon. So now there's some subsets containing 2 elements, about 1 and 2. How about 1 and 3, the set containing 1 and 3, and then the set containing 2 and 3. Is there another subset? 1, 2, and 3. So the set itself. I'm just going to call it A. We already have a name for it. Okay? Any questions? So we had 3 elements of the original set, right? The order or the size of A is 3. How many subsets did we get? 8. 1, 2, 3, 4, 5, 6, 7, 8. Wonder if would it be neat if there was a way we could calculate the number of subsets of a set if we already knew the size of the set? Yeah, so you see a connection between the number 3 and the number 8. There are 8 subsets, but 8 is 2 cubed. Two to the size of A subsets. And it's just a coincidence, huh? Maybe we should do about 30 more examples before we're convinced that this might be more than a coincidence. Well, here's an argument why this should be true. Okay, so I start off with a set with 3 elements, right? To make a subset, I've got to choose some of these elements. So for each element, I've got to choose. Should I include it in my subset or not include it? So it's either in or out of my subset. So I have 2 choices for each element. I can choose in or out of my subset, in or out of my subset, or in and out of my subset. When I make those choices, you can multiply the number of choices together, and you end up with 2 times 2 times 2 possible choices for subsets. So that's how you get 2 to the power 3 subsets. Here, I chose to exclude all 3 elements. Here, I chose to exclude 2 and 3. Here, I chose only the number 2, only the number 3. Here, I chose the number 1 and 2. And so you see, there's all the possible ways to choose 1, 2, or 3, whether to keep it or not. Okay. So the same, that same kind of argument would work for any finite sets. And really technically the number infinity is not a number, or the symbol infinity or the concept of infinity is not a number. But I kind of treat it as a number. So if you have an infinite set, you're going to have infinitely many subsets. Okay. But let's talk about this. So fact, if the size of set A is n, then A has 2 to the power n subsets. How could this be useful on like a homework problem? Say you had to list out all the subsets of a set. Maybe it'd be nice to know how many there were so you can see if you got them all. Right? So since it's the power of 2, you're always going to have an even number of subsets. It turns out it's always going to be a power of 2. Actually, I said it's always going to be even. That's not true. There's one set that has an odd number of subsets. I have the empty set. Yeah. Right. So how many? So let's list the subsets of the empty set. There, I did it. Because the empty set is a subset of itself, and every set is a subset of itself. But that's the same thing. I mean, I'm not going to count that as 2 different subsets. That's it. So the empty set is a subset of itself. that's the only one. So I should have said every set as a power of 2 number of subsets. Shouldn't say even.
And 0 then, right?
Sorry?
And in that case,
Yep.
it's 0.
Exactly. So right. So the size of the empty set is 0. So 2 to the 0 is 1. That's why there's only 1. All right. So the formula still holds. Still power of 2. Okay. All right. Now I wanted to look at what I got on the book. I can't pull it up on the computer. Let's see here. If you have your book, I'm on page 13. I mean, I'll just write them on the board here. Some examples. How about some statements? So here's some true statements. The book says, be sure you understand why the following statements are true. Each illustrates an aspect of set theory that you've learned so far. Okay? So, for example, like 1, let me just write it without saying it. Why is this a true statement? So how would you read this? So I stopped myself from reading it.
1 is not a subset of the set 1 comma set 1.
Yeah. 1 is not a subset of this set. So I'm telling you this is a true statement. You see why? Anybody? Sorry?
1 isn't a set.
1
Isn't a set.
isn't a set, exactly. So this is an element of this set, but the number 1 is not a set. Right? It would have to be a set over here. So another statement that is true, if I said this, 1 is an element of. Now this is a true statement. 1 is an element of this set, but 1 is not a subset of this set. Okay? So it's kind of making you just think precisely about the notation. This is just for sets. You can only compare sets with this notation. This, you can only, this is an element of. Okay? The empty set. Why is this statement true?
The set is nothing but natural numbers doesn't have nothing containing sets.
Sorry?
The natural number doesn't contain any set.
Yeah, so this is the elements of the natural numbers are numbers. They're not sets. So that's why this set is not an element of this set. Is the empty set a number? No, so it can't be a natural number. This says the empty set is not an element of the natural numbers. Okay, so if you read it, maybe it makes more sense. The empty set, think of it as like an empty box. Is an empty box a number? No. So this is true. What I could say, I could say this. The empty set is a subset of the natural numbers. That's a true statement as well. Right? Because the empty set is a subset of every set. Basically looking at the difference between element of, not an element of, and subset of, or not a subset. how about this? Why is this true? Make sure you get all your brackets and braces. So again, these are all true statements. You explain why this is true. This is the symbol for not a subset. This set is not a subset of this set.
Because your natural number set has numbers in it, and you have an empty set.
Okay. Yeah, so let's think about, yeah. For this, if this was a subset of this set, okay? If this was a subset of this set, then everything inside this set would have to be in this set. Okay? So what's inside this set? Inside the set is just one element, the natural numbers. Do you see exactly this symbol inside this set? No. If the thing that messes it up is these braces here. This element is not in this set, so it's not a subset. So this set is not a subset of this set. Now you see this. What's probably causing confusion is that you see this exact thing written right here, right? But right here, this is an element of this big set. So this set right here is an element of this set. So what I could have done, if I replace this with is an element of, this is still a true statement. This exact thing is inside this set. So this exact thing is an element of this set. Okay. Questions? A couple problems I want you to work on from this section. Just 2 problems. This is again homework for Monday. I posted this on Blackboard, page 14, number 2 and 12. It might seem like we're kind of piling up on homework problems here for homework time, but most of these are pretty short. When we get to writing proofs, I'll never give you 20 proofs to write, on one homework assignment. Okay, so but we're kind of stacking up here. Some homework problems so far. Okay. Any questions about subsets before we go on to 1.4? So 1.4 is pretty short, so we can knock that out today too. Section 1.4. Okay, so let me leave this example up from 1.3. Ooh. Too far. All right, here we go. So remember to do this example about subsets. So A is a set containing the elements 1, 2, and 3. How many subsets? We got 8. Right, here they are. Okay. What if I take all these subsets and put them in a set? Okay. That's pretty easy to do. There, did it. That is a new thing. That's a new set. Okay. This is the set of all subsets of A, right? So the set of all subsets of A. Okay? We call this the power set of A. Yes, question?
So the set of all subsets of A isn't a subset of A.
No, the things inside the set don't even look anything like those,
Okay.
right? Because now the elements of this set are subsets. They're not numbers like 1, 2, and 3. Okay, but A is a subset of this one because A is a subset of itself. Okay. So now the elements of this set are sets. In particular, they're subsets of A. This is called the power set of A. Okay. It's called the power set of A. Notation is like a cursive P. It kind of looks like a function notation. P of A. Okay. So that's notation for the power set of A. So this is another common. What's the object that's used? Set theory. Okay. So let me give a more formal definition. There's an example of a power set. This is 1.4. Power sets. The definition, let A be a set. The power set of A denoted by this cursive P of A is the set of all subsets of A. I'm already seeing one example. Take a set, you can figure out all the subsets of it, put braces around them, now you have the power set of A. Okay. So the power set of A, if I wrote this in set builder notation, it's a set of all sets X such that X is a subset of A. All right. We already know how big power set is, right? For a finite set, here's the notes. So remember, A had 3 elements. Turned out there were 8, or 2 cubed, to the size of A subsets. Okay. So if there's to the size of A subsets, and that's the size of the power set. That's how many elements there are of the power set. Okay. All right. So recall if the size of A is n, then A has 2 to the n subsets. Right? What we just said? So that's the size. So if A has size n, then the power set of A has 2 to the n elements. Okay. So therefore, the size of the power set of A is 2 to the n. Okay. Some people write like this, so the power set of A, the size of the power set of A is 2 to the size of A. Okay. So this is just a fact about subsets, right? There's this many subsets of A. So, well, the power set is just the set of all subsets. So the size of the power set is the same as the number of subsets. This notation, some books, some mathematicians actually kind of use this idea for the notation for a power set. Some books write 2 to the A as the power set of A. You can see why. I mean, if this is the power set of A, then the order or the size of the power set is 2 to the size of A. Some people write this for the power set. Well, I'm going to stick with book's notation, like script P of A for the power set. Okay. An example. Suppose the size of A is 3, so set A has 3 elements. And set B has 5 elements. Okay. So find the size of the power set of A. So another way of saying this is how many subsets does A have? If the size of A is 3, how many subsets does A have? 8, right? Remember it was the formula for subset, it was 2 to the order, 2 to the size of A, or 8. You see how I could have said how many subsets this has, or I could have said what's the size of the power set of A. Those mean the same. You get the same answer. Okay. How about what's the power set? What's the size of the power set of B?
32.
2 to the 5th is 32. Okay. So, kind of, that's about the threshold of a set that a discrete math professor would require students to do on a homework assignment. I mean, you get 32 sets. I mean, we're starting to get just too much. Okay, so, all right. So this power set, if I said, oh, here's a set with 5 elements, list the power set of B. As we're already getting up to 32 elements. Okay, how about this? I require A cross B. So the Cartesian product. So think about Cartesian product of A and B. Remember, you take elements of A for the first coordinate, elements of B for the second coordinate. So how many elements are in A cross B? 15, right? 3 times 5. So the power set of a set with 15 elements would be 2 to the 15. Which you all know is
42,700.
clearly 32,768. Okay. So, you guys behave yourselves. I won't put that on a homework problem. All right, you got a 15-minute quiz. Write all the subsets of the power set, or just write the elements of the power set of A cross B. Okay. How about this? Okay, so we know the power set of A has 8 elements. What if I took the power set of A? So you don't have to list it out. I just want to know how many elements are there. What's the size of the power set of A?
2 to the second to the third.
Is it? 2. Are you saying 2 to the second, which is 4, to the power of 3? Is that what you're saying?
That was our basically saying 2 to the second, which is, or in that second to the third, so it'd be 2 to the 8th.
2 to the 8th, you're saying. What do you think? So, how many elements does power set of 8 have? 8, right? So the power set of any set with 8 elements will have 2 to the 8 elements. Okay? So you see what he was saying, 2 to the 2 to the third. Is 2 to the 2 to the third the same as 2 squared to the third?
So it'd be 2 to the 6th.
Yeah, because if you multiply these exponents, that'd be 2 to the 6th, so it's not the same. That's 2 to the 8th. So yeah, when you say 2 to the 2 to the third, it's probably better to say 2 to the 8th. Right? That's big for now. Or you have to do 2 to the parentheses to the third. Okay. All right. How about, so what's 2 to the 8th? 156. All right. How about this? The power set of A cross the power set of B. How many elements would there be in this set? Eight times 32. Yeah. So for a Cartesian product, you just take the elements of this set times the elements of this set, and that'll give you the size. So we already did this in step 1 here. There's 8 elements here. There's 32 elements here. So think of it this way: 2 cubed times 2 to the 5th, so it is 2 to the 8th, or 256. Okay? Any questions? No questions, huh? Homework from this section. Page 16, number 2, 8, 14, 15, 16. I guess it's a good thing you guys already started homework, right? So thank you so much. So really, if you haven't started your homework, you'll see that a lot of these problems aren't that long at all. Like this is like a homework problem here. Power set of A is 8. I mean, it's not like it's going to take you that long. Yes, question.
Do we put all of these homeworks on the same picture?
Sure. Yeah. Yeah, you don't have to do 4 separate sheets of paper. This is all one assignment. It's all, all the problems. The thing is, instead of, when we finish a section, I'll assign homework from that section. Okay? So then all those homework that I've assigned that week, you're going to turn them all in on Monday. Okay? And I did post this assignment on the Blackboard website, all these homework problems. Okay?